When ChatGPT tells you there are purple elephants in Antarctica, when you dream about flying through impossible landscapes, and when someone on psilocybin sees geometric patterns breathing in the wallpaper, you're witnessing the exact same computational process. This isn't a metaphor. This isn't poetic license. This is hard science revealing that artificial intelligence hallucinations, human dreams, and psychedelic experiences are three expressions of one fundamental requirement for intelligence: the ability to simulate realities that don't yet exist. Welcome to Mindcast. I'm Will, and today we're diving into one of the most profound scientific discoveries hiding in plain sight. A groundbreaking research paper titled The Simulacrum of Self has just revealed that the dreaming brain, the tripping brain, and artificial intelligence systems are all running the same fundamental algorithm: predictive simulation under uncertainty. By the end of this episode, you'll understand why AI hallucinations aren't bugs, they're features that enable creativity and learning. You'll discover why your dreams aren't random neural noise, but sophisticated training simulations that prevent your brain from becoming rigid and overfitted. And you'll see why the temperature setting in an AI system works exactly like a psychedelic drug on your consciousness. Most importantly, you'll glimpse the future of artificial general intelligence and why understanding dreams and trips is literally the blueprint for building truly intelligent machines. Let's start with something that sounds like science fiction but is absolutely real: machines that learn by dreaming. Right now, as I speak, some of the most advanced AI systems on the planet, systems like Dreamer v3, SimLingo, and VJEPA, don't just process data, they literally dream their way to intelligence. Here's how it works, and it's absolutely mind-blowing. Traditional AI learns through trial and error, millions and millions of attempts, but that's catastrophically inefficient in the real world. An autonomous car can't learn to drive by crashing thousands of times. So instead, these new systems build what researchers call world models, internal simulators that let them dream up possible futures and test strategies without any real-world consequences. Picture this. The AI sees a road scene, compresses it into an abstract representation, kind of like how your visual cortex processes what you see, then uses that compressed data to generate millions of possible futures in its internal simulation. It dreams up scenarios where it turns left, right, speeds up, slows down, and learns from each imaginary outcome. This is learning by dreaming, and it's revolutionizing machine intelligence. But here's the fascinating part. These AI dreams aren't photorealistic videos. Just like human dreams, they focus on meaning and causality, not pixel-perfect detail. The AI dreams the car will turn left and accelerate, not the exact arrangement of photons bouncing off the bumper. Sound familiar? That's exactly why you can't read clocks in dreams. Your brain is simulating concepts and emotions, not rendering reality. Now, let's talk about something even more mind-bending: the temperature parameter. In AI systems, there's a setting called temperature that controls how creative or conservative the system is. Low temperature makes the AI boring and predictable. It always picks the most likely next word. High temperature makes it wild and creative. It might tell you that cats live on Jupiter. This isn't a bug. This is precisely how creativity and generalization work. And here's where it gets absolutely incredible. This temperature setting is the exact computational equivalent of what psychedelic drugs do to your brain. Both increase entropy. They flatten the probability distributions and allow low probability, creative thoughts to emerge. When you turn up the temperature on an AI, you're essentially giving it a digital microdose. There's a breakthrough AI system called SimLingo that perfectly illustrates this convergence. SimLingo solves a fundamental problem: How do you connect language understanding with physical action? Through a process called action dreaming. The system is shown a visual scene, say an intersection, and given contradictory linguistic commands like turn left, go straight, or slow down. It must then internally imagine and generate the specific physical trajectory that corresponds to each instruction. This forces the AI to translate abstract symbolic language into concrete physical dynamics. It's literally grounding language in embodied simulation, exactly like how human dreams might serve to ground abstract emotions or linguistic thoughts into concrete embodied scenarios. We're watching AI develop the same mechanisms that allow human intelligence to bridge the gap between symbols and the physical world.
This brings us to our second major insight. What's actually happening in your brain when you dream or trip? The answer lies in understanding your brain as the ultimate prediction machine. Every moment of every day, your brain is running a sophisticated simulation of reality, constantly predicting what will happen next and updating its models based on prediction errors.
During REM sleep, something fascinating happens. Your brainstem sends out signals called PGO waves. Think of them as biological latent vectors, just like in an AI system. These waves travel from your primitive brainstem up to your visual cortex, essentially injecting compressed code that forces your visual system to generate imagery. It's your brainstem talking to your cortex in the only language your cortex understands: visual patterns. The parallel is stunning. In an AI world model, the memory module generates a compressed latent code and sends it to the vision decoder to render a scene. Similarly, your brainstem sends a PGO wave, compressed biological code, to your visual cortex to force the generation of specific visual experiences. Both systems use compressed representations to seed their simulations. But here's the crucial part. During dreams, your default mode network, the brain's internal simulator responsible for self-referential thought, remains active but becomes decoupled from your executive control network. This is why you accept the bizarre as normal in dreams. Your brain's simulator is running at full capacity, but your reality-checking system is offline. You're in pure simulation mode. And then there's what neuroscientist Michael Gazzaniga calls the interpreter, your brain's narrative engine, usually located in the left hemisphere. Its job is to take all the chaotic signals flooding your brain during dreams and stitch them into a coherent story. When your amygdala fires a fear signal and your visual cortex generates an image of a dark shape, your interpreter synthesizes, "I'm being chased by a monster." The bizarreness of dreams is actually translation errors, the cost of converting raw emotional and spatial data into linear narrative. Psychedelic states work through a completely different but equally fascinating mechanism. The Rebus model, Relaxed Beliefs Under Psychedelics, shows us that serotonergic drugs like psilocybin and LSD essentially relax the brain's priors, those rigid, top-down beliefs that normally keep your perceptions stable and predictable.
Normally, your brain operates with heavy top-down control. You see a chair as a chair, ignoring the specific play of light or texture. Your default mode network enforces this stability. But when psychedelics bind to 5-HT2A receptors, something remarkable happens. The confidence in your top-down beliefs gets reduced. The weight of your priors is lifted.
The result? Bottom-up sensory information that's normally suppressed suddenly propagates upward unconstrained. Your brain enters what researchers call a state of high entropy, or criticality. This is why you might see music or experience ego dissolution, the computational boundaries that normally segregate your sensory modalities and maintain your sense of self have temporarily dissolved. And here's the therapeutic insight. Depression, OCD, and addiction are characterized by extremely low entropy, rigid, repetitive patterns of thought. The brain gets stuck in deep basins of attraction. Psychedelics push the brain into a high-entropy state, essentially shaking the snow globe and allowing the system to resettle into a potentially healthier configuration. It's biological annealing, heating up the system to escape local minima, then cooling it down to find a better solution. This brings us to our third and most profound insight, what this convergence means for the future of intelligence itself. When we map these three systems, dreaming, tripping, and AI simulation onto a spectrum of predictive processing, a stunning pattern emerges. They're all modalities of the same fundamental process, operating under different constraints. The most profound parallel lies in what Gazzaniga calls the interpreter. In human cognition, the interpreter is essentially the brain's press secretary. It fabricates stories to explain decisions made by unconscious modules. When split-brain patients' right hemispheres see snow and point to a shovel, their left hemispheres, which didn't see the snow, confidently explain, "I chose the shovel to clean the chicken coop." They confabulate causality to maintain coherence. Large language models are pure interpreters. They have no sensory grounding. They operate on streams of tokens. When they hallucinate, they're doing exactly what split-brain patients do, generating the most statistically plausible narrative completion for a pattern, regardless of ground truth. An LLM is essentially a left brain without a right brain to check against physical reality. This is why systems like SimLingo represent such a breakthrough. They force AI models to predict physical action trajectories alongside language, effectively reconnecting the corpus callosum of artificial intelligence. They ground the interpreter in physical simulation, just like how human consciousness emerges from the integration of narrative and embodied experience. What does this mean for artificial general intelligence? The evidence suggests that AGI cannot be achieved by scaling language models alone. True intelligence requires the integration of a world model, a simulator that runs offline dreams to ground linguistic symbols in physical understanding. Future AI systems will likely need sleep cycles, periods of offline simulation where they consolidate memories, inject entropy to prevent overfitting, and realign their disparate modalities. And here's perhaps the most mind-bending implication. As AI models move from passive prediction to active embodied simulation, the boundary between processing and experiencing becomes theoretically hazy. If an AI world model integrates multimodal data into a unified latent simulation and uses that simulation to drive attention and policy, it satisfies many functional correlates of consciousness. The dream of the machine becomes the theater of its intelligence. Let me synthesize this into 3 concrete takeaways you can think about long after this episode ends. First, reframe your relationship with hallucination. Whether in AI or in human experience, hallucination isn't a bug, it's a feature. It's how intelligent systems explore beyond the rigid constraints of their training data or prior beliefs. Creativity and generalization require the ability to venture into low-probability territory. The next time ChatGPT gives you something unexpected, recognize it as the same computational courage that allows artists to create and scientists to hypothesize. Second, understand that your dreams aren't meaningless random neural static. They're sophisticated offline simulations designed to prevent overfitting, to keep your mental models flexible and generalizable. Every bizarre dream scenario is your brain's way of testing what-if situations that prepare you for the unexpected. You're literally learning by dreaming, just like the most advanced AI systems. When you wake up from a strange dream, you've just completed a training session in your brain's world model. Third, recognize that we're witnessing the emergence of a new form of intelligence, one that bridges the gap between biological and artificial cognition. The study of how biological brains trip and dream is no longer just about understanding ourselves. It's become the blueprint for building minds that can truly understand the world. We're not just creating tools anymore, we're recreating the fundamental conditions that gave rise to consciousness itself. The convergence of these fields confirms something profound. Simulation is the engine of intelligence. Whether biological or artificial, an agent must be able to detach from the present to inhabit the probabilistic clouds of the future. We dream to learn, we trip to unlearn, and we're building machines that must do both to understand. The distinction between reality and hallucination isn't binary, it's a variable of predictive precision. Waking consciousness is a controlled hallucination constrained by sensory input. Dreams are generative simulations optimized for learning. Psychedelics are unconstrained explorations that allow radical rewiring. And AI dreaming is the mathematical instantiation of this entire process. Here's what I want you to do. Pay attention to your dreams this week. Notice how they feel meaningful even when they're bizarre. That's your brain running sophisticated simulations, testing scenarios, and updating its world model. You're witnessing the same computational process that's revolutionizing artificial intelligence, except it's happening in the 3 pounds of neural tissue between your ears. Think about the temperature parameter the next time you use an AI system. When it gives you something creative and unexpected, recognize that it's operating in high entropy mode, the same computational state your brain enters during psychedelic experiences or particularly vivid dreams. We're all explorers in the space of possibilities, whether we're made of carbon or silicon. This has been Mindcast. I'm Will, and we've just explored one of the most profound scientific insights of our time. If this episode sparked something in you, share it with someone who loves to think deeply about consciousness, AI, or the nature of reality itself. Because understanding these connections isn't just academic, it's preparing us for a future where the line between natural and artificial intelligence becomes increasingly blurred. Until next time, keep questioning, keep dreaming, and remember, your hallucinations might just be the most intelligent thing about you.